information. Uninformed search was blind search. So we start with approximation. Now in constraint satisfaction algorithm, we have received or we are knowing particular condition, and if we satisfy that condition, then we can move towards the goal. So this is what called as goal test. Now first of all, constraint satisfaction algorithm is greatly applicable in computer engineering, robotics, everywhere. Now the problem is generally having problem space or configuration space. CSP configuration space is there. In that we are having, it's like black box structure, and now each move of the variable is state or current state, previous state and next state. Then domain, that means where problem is being operated. Domain decides what type of cost will be there. For example, if you are looking at distances, then domain will be distance. If you are looking at colors, domain will be color. Similarly, so domain is required because domain knowledge will be considered at that point, because the constraints for goal test will be from domain. Now goal test is the set of conditions or set of constraints or allowable combination of values that can be applied, and every time we check whether goal is achieved or not. Now this algorithm is greatly used for many problems like map finding, coloring the maps, or you are having finding a particular conditions for robotic movements. Now this is a simple example we have taken. So now you are having a rectangle. So this is geometrical problem, and again it is color based problem. So we have to apply colors. So there are three colors and four variables are there. Three colors and four variables are there. These four variables are vertices of this rectangle. So we are having A, B, C, D, like four modes, right? Now we are up to apply RGB to this. Now constraint, that is the condition. So all neighbors of corners must have different colors. There should not be similar type of color. Now constraint satisfaction algorithm is one having one more property, that is what called as backtracking. Many times when problem is simple, we can assign and straight away go and solve the constraints. But whenever there is a conflict, for example, we start now allocating colors. So we assign first corner red color, second corner we assign now green color. Now while assigning blue color, see now we are having overlap. So if I apply blue, then there will be problem. So what we do, we go to next state and look back to previous state. This is what called as backtracking. So we consider sum of or single next state and again solve or resolve the constraint. So this is how backtracking work. We'll see backtracking in details. Right now we will go for constraint satisfaction. Simply the backtracking idea is that, so for a simple conditions, all constraints can be applied, but whenever there will be overlap, whenever there will be conflict, at that time we have to resolve conflict wherever two or one more combinations are there. So we have to resolve by going ahead and then we have to look back. That's why it is backtracking. So we assign color first to D and then we go for C. This is how we can resolve this problem. So we are going ahead and then looking back. That's why it is backtracking. Now this classical application is used in map coloring. So just same principle we are using over here, right? This is how node chart is there. I'll not explain this in details. And then you can assign. So here also condition is that all states must have different color. and no two neighboring states should have same color. This is what constraint over here. Okay, so in this example, look at variables are different states. The domain is three colors. Constraint is that adjacent regions must have different colors. Simply, we have to solve this problem by making many times equations also. So we have to again generate successor step based on equations. So we can solve that constraint by having equations. Next type of problem is crypto arithmetic. Now this problem is important for us because we are many times doing instruction formation. So we form instructions or we assign particular string and we assign a particular numbers, and then we use such type of instruction in robotics in many of programming languages. So now backtracking, we are discussing backtracking. Already we have discussed many times. Backtracking is a special property of CSPs. So whenever backtracking is applied in a search of the trees, that is our node structure, at that time, now it gives you power to go to next branch and or next layer, and you can look back, and again you can adjust the values by going some next values, right? So better search tree will be constructed using CSPs. So backtracking is special and powerful property of constraint satisfaction algorithm. Now this is simply because there are constraints. Many constraints are single condition, but whenever there is a possibility of violation, we have to consider next states or next many states. So this allows special power that you can go ahead and come back. In all of previous algorithm, this is not possible because in tree I can take only one position and I have to resolve that position, right? And every time what happens, I am going ahead considering the combination and assigning or considering best path of nodes which are behind also. That is not possible in terms of our conventional algorithm, informed and non-informed search. So backtracking is a special property, right? Here, even though you are at this node, next nodes can be considered, and then we can find better path. So this power is given to the backtracking algorithm. Here is that recursive or backtracking algorithm is explained, right? Here you can consider the constraints and go ahead. That is, many conditions can be constrained.